Good morning friends. Today we are going to deal about hypoxia part 2. So we know what is hypoxia? Hypoxia is that there is less oxygen in the tissues, right? So it can be caused by, we studied a certain equation, cardiac output plus 1.39 into hemoglobin concentration into percent saturation of hemoglobin plus 0.003 into PaO2, right? We have learned this. This is the equation for oxygen delivery to tissues. So if oxygen delivery to tissue is decreased, then hypoxia happens, right? We have learned that cardiac output reduces in heart failure, hemoglobin concentration reduces in anemia, percent saturation of hemoglobin reduces in what? Carbon monoxide poisoning or methemoglobinemia, right? So we have learned all this stuff where oxygen delivery to tissue is being reduced. Understand? Now, what is other thing that causes hypoxia? Hypoxemia. It is hypoxemia. We learned this. So, in hypoxemia, we divide it into two categories. One with perfectly normal AA gradient. That is normal AA gradient. But in some places there is what? The other category is AA gradient is increased. Okay, normal AA gradient and increased AA gradient. Let's see what's the difference. If AA gradient, what was AA gradient? We have learned this, that there is alveoli, capital A stands for alveoli, small a stands for artery. So here, we know that we take oxygen inside, so there is a partial pressure, it's known as alveolar partial pressure of oxygen, and when it comes here, it is arteriolar partial pressure of oxygen. So we know there is diffusion here. So if mostly the 100% of diffusion should happen, but because of mixing with the shunting blood, the partial pressure of oxygen is reduced here. But thing is that if it is very much reduced, if it is like very different, there is a more difference between partial pressure of oxygen in the alveoli and partial pressure of oxygen in the artery, that means something is wrong with the diffusion. Understand? Something is wrong with maybe with the alveoli or maybe with the artery. So something is wrong with any of this, can cause increase in the AA gradient. What was AA gradient? Difference between PaO2 and P small a2. Understand? So if that is there, diffusion has some problems and it will be increasing. What will be increasing? AA gradient will be increasing. Understand? So if AA gradient increases, that means something is wrong with the alveoli. But if the AA gradient is normal, that means nothing is wrong with the alveoli. Alveoli is functioning perfectly. The lung is functioning. Lungs function is normal. But thing is that there is something wrong with inspiration. Maybe what? It is respiratory rate reduced. Reduction in the respiratory rate or hypoventilation, right? Or maybe because the muscles that is required for inspiration has some problems, like neuromuscular diseases. Neuromuscular disease, like myasthenia gravis or AML or something like that. Otherwise, it may be because they are in the higher altitude. If that person is in high altitude, the partial pressure of oxygen and carbon dioxide in the high altitude are very less. So obviously the partial pressure inside the alveoli will be less, and then partial pressure in the oxygen in the artery will be less, right? So that happens. So that means something is wrong with the inspiration. AA gradient is wrong. What if AA gradient increases? If AA gradient increases, that means they undergo multiple mechanisms. It can be multiple mechanisms. Let's say one is dead space, other one is V by Q mismatch, diffusion limitation, and shunting. Okay, we will have to learn about dead spaces, V by Q mismatch, diffusion limitation, and shunting one by one, and let's see into that. Okay, now we are going to deal with hypoxemia with increased AA gradient. Right. increased AA gradient. So for better understanding, let me divide the lung into 3 parts. Okay. So here we have 3 parts, and here we have dead space. This dead space. Here we have shunting. Here we have V by Q mismatch. Okay. So we'll be dealing with each one. First of all, dead space. What is dead space? We know that there are 2 types of dead space: anatomical dead space and physiological dead space. Anatomical and physiological. I've told you all this, that's why I'm telling it very fast. But we know what is anatomical dead space. Here we have trachea, bronchi, bronchiole, and terminal bronchiole, right? Bronchi, bronchiole, terminal bronchiole, up to terminal bronchiole, it was conducting zone or anatomical dead space. Understood? And what was physiological dead space? It was addition of anatomical dead space plus alveolar dead space. What was alveolar dead space? Alveolar dead space are those places which alveoli does not have blood supply. Understood? So what makes a dead space dead space? Actually, it is that those places that does not have blood supply. Here we don't have blood supply. Up to terminal bronchiole, we don't have blood supply. From respiratory bronchiole, we know that from here respiratory bronchiole is there, the alveolar duct is there, sac-like structure is there, alveoli is there, right? So from here only we have what? We have the blood supply. Therefore, those places does not contribute to dead space. But in some places alveoli does not have blood supply, that contribute to alveolar dead space. So together, those places that does not have blood supply together contribute to physiological dead space. And we know how to calculate physiological dead space. It is equal to Vd is equal to 80 into PaCO2 minus PeCO2 by PaCO2. So we know this thing, right? It was Bohr's formula of calculating physiological dead space. Okay. So we know what is physiological dead space, what is anatomical dead space. We know what is dead space, right? Dead space. Those places which do not contain blood vessel, which has something wrong with the blood vessel. So we said AA gradient increases, that means something is wrong with diffusion, maybe something wrong with the alveolar, maybe something wrong with the blood vessel. So here we have blood vessel, something is wrong with the blood vessel, that is dead space. Understood? Now let me talk about shunting. What was shunting? We know that there is in tissues or in alveoli, here when we say alveoli, we have capillaries, right? In alveoli we have capillaries. So arteries come and capillaries form and then venous system. But in some places, this blood vessel, some blood vessel, bypasses the alveoli. Understood? They bypasses the alveoli. So therefore, actually alveoli is waiting to for a blood vessel to come. Blood vessel coming with the blood. So what alveoli give? Alveoli give the oxygen and take the carbon dioxide and go. But thing is that now alveoli is not there, and blood vessel is searching for alveoli because he need oxygen, but he is not getting oxygen. So what happens? There is less oxygen in the blood. Hypoxemia happens, right? So here there is less oxygen in the blood. Hypoxia happens. Understood? So it is what happens here. Either alveoli is not there, or maybe alveoli has some problems. That's why the ventilation is not there. Understood? So what is the problem here? Something is wrong with the alveoli. Maybe alveoli is not there, or maybe something wrong with the alveoli. Mucus plug or something. So because the air cannot reach here. Understand? So maybe it is because alveoli is not there, maybe something is wrong with the alveoli that contribute to shunting. Understand? So what are the pure shunt? What are the pure shunts? You know that it is ventricular septal defect or atrial septal defect, right? All these are pure shunts. Where is those shunts seen? In heart actually. Heart is here. This is atrial septal defect. This is ventricular septal defect. Right? Here we have atrium and here we have ventricle. If septal defect is there, there is shunting of blood. Understood? It is not going into the lungs. It is bypassing those lungs. Okay. So we know this thing. So that means shunting contribute to less oxygen, hypoxia. And dead spaces contribute to increased carbon dioxide. So see, what contributes in increasing carbon dioxide? Actually, carbon dioxide should be removed by ventilation, right? But here alveoli is there, but there is no blood supplied to that places. So actually the person who have to carry the carbon dioxide and give it to me is not coming. Then how can carbon dioxide, get outside? So carbon dioxide will increase in dead spaces. So that's very important. That means in dead spaces there is what is carbon dioxide increasing called? Hypercapnia. There is hypercapnia in dead space, and there is hypoxia in shunting. Understood? This is very easy. And see, in physiologically, when we consider the lungs, we have to see what is V by Q. What is V by Q? V by Q. V stands for ventilation, Q stands for perfusion. Understood? V stands for ventilation, the amount of air that we breathe, and Q stands for perfusion. Okay. Now V by Q, V is 4 and Q is 5, so 4 divided by 5 is equal to 0.8. This is a normal value. What is the ideal value? 1. Ventilation and perfusion equally. Understand? Those are becoming equal, and V by Q will be 1. That is the ideal condition. Here normally it is 0.8. Let's see. Here something is wrong with the blood vessel, right? So there is something wrong with the perfusion. That means this is decreased. Understand? If this is decreased, if Q is decreased, V by Q will increase, right? So that is the logic of mathematics. So V by Q, when V by Q increases, what happens? It is 3 here, it is 2, it is 0.8 here, and it is 0.6 here. Okay? So this is how physiologically from upper portion of lungs to the lower portion of lungs, this V by Q value decreases. Understood? It's very easy to understand now. And normally, see, when we ventilate, let's get this logic that air is something that ventilation is something that goes up, right? Air is something that rises up. So ventilation is more in this portion. Oxygen is more in this portion. Understand? Here, oxygen is there. Ventilation is there. Here, something is wrong only with the perfusion. Here, perfusion is there. Something is wrong with the ventilation. So ventilation is there here. There is enough oxygen here. So ventilation is more, 3. Here perfusion is less, so 0.6. Okay. Sorry, perfusion is there. Here ventilation is less. Understood? So when this is increased, V by Q will be decreased, 0.6. That's it. And see one more thing. So let's consider V by Q of dead space, V by Q of mismatch, and V by Q of shunting. Let's see V by Q of dead space. In pure dead space, we don't have perfusion, right? Perfusion is equal to 0. That means Q is equal to 0. Anything divided by 0 is infinity. So V by Q in dead space is equal to infinity. Understand? And in shunting, we know that there is something wrong with the alveoli. In pure shunt, what are the examples of pure shunt? It is ASD or VSD. What was ASD and VSD? Arterial septal defect and ventricular septal defect. We told this thing, right? So if ASD or VSD is there, that means there is no what? There is no alveoli. There is no ventilation. If there is no ventilation, V is equal to 0. So V by Q will be 0. If V is equal to 0, 0 divided by anything is 0. So here V by Q is equal to 0. Understood? Very much more decreasing. 3 decreasing physiologically and pathologically. It decreases from upper portion to lower portion. And we are comparing physiologically and pathologically, so that we understood everything equally. We don't want to confuse anything. Understand? So let's draw this diagram again. and also we'll be dealing with V by Q mismatch. So see, we have lengths here. We divided into 3 parts. This is dead space. This is V by Q mismatch, shunting, and physiologically we have V by Q equal to 0. Here it is 3, here it is 0.8, here it is 0.6. Okay. And examples of dead space are pulmonary fibrosis. He said it is something wrong with the blood supply, right? So pulmonary fibrosis is fibrosis of the endothelium of a blood vessel. And pulmonary edema, emboli. Pulmonary emboli, that is a clot in the blood vessel. Okay? So pulmonary fibrosis and pulmonary emboli can cause dead space pathologically. And V by Q mismatch example is pulmonary edema. What is pulmonary edema? There is fluid inside alveoli. If there is fluid inside alveoli, here V by Q will be decreased less than 1. And we said if there is no enough ventilation, the blood supply will be taken to normal places. So here V by Q will be equal to 1. Understand? So this will cause what? V by Q mismatch. Here it is less than 1, here it is 1. So that's why it is causing V by Q mismatch. Pulmonary edema causes V by Q mismatch. And shunting, we said in shunting there is pure shunt which is caused by ventricular septal defect, atrial septal defect. Those causes shunting. And also, see, we said it's something wrong with the alveoli, right? Something is wrong with alveoli, or maybe alveoli is not there. So if alveoli is not there, that means it is a pure shunt and ventricular septal defect or atrial septal. Or maybe the respiratory tract has something, blocking the ventilation. What is that? Maybe a peanut that the child aspirated. So maybe a peanut block, peanut inside the respiratory tract. That causes shunting. Understand? So those are the examples of each dead space, V by Q mismatch and shunting. I hope you understand. And also we said in dead space there is something wrong with the Q. That is the perfusion, it is reduced. And pure dead space, that means what? The Q is equal to 0. That means V by Q is anything divided by 0 is infinity. And here we said that shunting, there is something wrong with the alveoli. That means something is wrong with the ventilation. If it is a pure shunt, that means V is equal to 0. That means V by Q is equal to 0. So that's why I'm saying I don't need you to by heart anything here. I need you to understand why it became like this. If you understand that dead space is actually something, some places which does not have blood supply, those respiratory tract paths which do not have blood supply, then everything will come into your brain. If you understand what dead space is, and if you understand what shunting is, you will know everything. It will be very easy for you to understand and then memorize everything, because memorizing is not the way I do. I understand the things. Okay. Anyway, it differs from person to person. Anyway, the next topic is partial pressures. Here we said there is something wrong with the blood vessel, right? So here the alveolar pressure will be more. Alveoli is working perfectly. So alveolar pressure will be more than arteriolar partial pressure, more than venous partial pressure. And in here, arteriolar partial pressure will be more than alveolar partial pressure, which is more than venous partial pressure. Again, next, it is that this is fine, blood vessel is fine, something is wrong with the alveoli. That means alveolar partial pressure will be very less than venous partial pressure, which is less than arterial partial pressure. Understood? It's very logic. So now with that logic itself, we got the partial pressures, right? Okay. We got the pressure zones, right? So we understood every zone. Those are the pressure zones. Upper portion of the lungs, middle portion of the lungs, lower portion of the lungs. We understood where the arterial partial pressure is more and where the alveolar partial pressure is less. Very easy to understand now. Okay. Now there are particular stuff that you have to understand. That we know about tuberculosis. What happens in tuberculosis? Tuberculosis are those bacteria that comes into more oxygenated places. So tuberculosis will be more seen in these places, right? Because here it is well ventilated. There is enough oxygen. Here ventilation is not getting. Otherwise, think about this. Oxygen rises upwards. So oxygen will be more. Or ventilation rises upwards. So ventilation will be more here. So there will be more oxygen at that place. So therefore tuberculosis goes and binds in there. That's one thing that you have to understand. And the other thing is that most of the pathological conditions will have multiple mechanisms. Not only one mechanisms. It will be having multiple mechanisms. Except pulmonary emboli, which is a pure dead space. Understand? And ventricular septal defect and atrial septal defect. It has only shunting. The mechanism is shunting. Okay, and peanut, they also shows shunting. So we understood, those mechanisms only showing one mechanism. Those pathological conditions showing only one mechanisms, right? Okay. We understood that. We understood the pressure zones. We understood about tuberculosis. We understood about each dead space. What is V by Q mismatch? What is shunting? So thank you guys for listening. It's been a wonderful day. We have dealt with hypoxia. In the next chapter, we will be dealing with carbon dioxide. If you have any doubt, any queries, please do inform me in my Instagram ID or WhatsApp number. And if you like this video, like, comment, subscribe and do the necessaries. So till then, goodbye and good luck.